Hi everyone, we're going to talk about acid-base titrations, and there are three types that I'll let you read here on your own. In this video, we're going to do an example of the titration of a weak acid and a strong base, but no matter what type of titration we're doing, our goal is going to be to calculate the pH at any point in the titration. So let's see if we can do it. Here's our example. We've got 0.1 formol sodium hydroxide, and in our Erlenmeyer, we've got 0.05 formol of some generic weak acid. We're given the Ka, and we've got 50 mils of it. And they're asking us to calculate the initial pH, and they're referring to the initial pH of this weak acid here. And before we do that, I always, when faced with these problems, just as a reference so I don't get confused, I like to write down the titration reaction. So OH is being added, and it's reacting with HA to form water and A minus. And then I also like to calculate the equivalence volume, or V sub EQ, just so I know where I am during the titration. The equivalence volume is the volume of sodium hydroxide needed to react with all of this HA here in this Erlenmeyer. And because these numbers are so nice and neat, you probably don't have to do any calculations to get the equivalence volume. You can see here that the OH concentration is twice the HA concentration. So if we have 50 mils of HA, we would only need 25 mils of OH to get the equivalence volume. Another way you could get the equivalence volume would be to use C1. You would be solving for V1, and you could call this C2 and this V2. And that will only work if your stoichiometry here is 1 mole to 1 mole. The way that I calculate equivalence volumes when these numbers aren't so obvious or nice and neat is I use solution stoichiometry. So if we have 0.0500 formol HA, that's moles of HA per liter, and if we have 50 mils, that's 0.0500 liters. We know that for every 1 mole of HA, it'll react with 1 mole of OH, and we know the concentration of OH, 0.1 moles of OH for every liter, and then convert liters into milliliters, and that should also give you 25 mils. But back to getting the initial pH, we've got the pH of a weak acid. We know that weak acids dissociate into H plus and A minus, and you know I'm going to use quick and dirty, but just in case quick and dirty fails, I like to write down what I have at equilibrium. That would be 0.0500 formol minus X for HA, X for H plus, and X for A minus. But let's try it. H plus equals the square root of Ka times the formol concentration of HA. And when I got H plus, I got 4.42 with an insignificant 2 times 10 to the negative fourth molar H plus, and that was, or is, 0.9% of the formol concentration of HA. So quick and dirty works. If you take the negative log of this H plus concentration, you'll get 3.354 for your pH. And remember, if we have 3 sig figs in N, we need 3 digits in the mantissa of A. So we got the initial pH. What's next? Well, now they want us to calculate the pH after 10 mils of OH have been added, and what will be in this solution after we've added 10 mils of OH? Well, note that this is before the equivalence volume. So that means that every time we add OH, it got consumed. So before the equivalence volume, what we have in this solution here is a solution containing HA and A minus. That's a buffer, or as Harris says, aha, a buffer. So if we could just figure out how many moles of HA and A minus there are, we could use the Henderson-Hasselbalch equation to get the pH. And I'm going to make an ice table in order to figure out how many moles of HA and A minus I have after adding 10 mils of sodium hydroxide. So initially, if we add 10 mils of 0.1 formol, that would be 0.00100 moles of OH. And initially, how many moles of HA are there? Well, you know the concentration, you know the volume. That would be 0.00250 moles. And initially, you don't have any moles of A minus. So now notice that OH is your limiting reactant. You'll subtract those moles from reactants and add them to the products. So that at equilibrium, OH got consumed as we thought it would. We have a little bit of HA left, 0.00150. And we've made some A minus, 0.00100 moles. So now we could use the Henderson-Hasselbalch equation, pH equals, well, you'll have to get the pKa. I got 5.408 for the pKa, plus the log of A minus over HA, and that gives a pH of 5.232. And it's nice to see that the pH did increase from that initial pH of about 3 after you've added a strong base. So that's how we do it before the equivalence volume. What's next? Well, it looks like they want us to do it, calculate the pH at the equivalence volume. And what's true at the equivalence volume? That means we've added just enough OH to react with all of the HA. So OH is gone, HA is gone. All we have left then in this solution is A minus. How do you get the pH of A minus? That's a weak base, and we should know how to do that. All we have to do is figure out the concentration of A minus at this point. So I'm going to make an ice table to do that. The initial moles of OH should be 0.00250. The initial moles of HA aren't ever going to change in this problem. And the initial moles of A minus are 0. Notice that the moles of OH are equal to the moles of HA. We're going to subtract those moles from the reactants and add them to the products. So that at equilibrium, OH is gone, HA is gone, and we've got 0.00250 moles of A minus. So that is a weak base. And you know how to find the pH of a weak base. Who cares that this weak base was produced in a titration reaction? Let's try quick and dirty. OH is going to be equal to the square root of KB. Well, they didn't give it to us, but you've got to get it from this KA and KW. I got 2.5 with an insignificant 6 times 10 to the negative 9th. And again, I only have 2 sig figs in my KB even though Ka had 3, because I only used Kw with 2 sig figs. And now we need the formal concentration of A minus. Well, that would be the moles of A minus that were produced over the total volume. So we started off with 50, we added 25, that's 75 mils, or this many liters. And I got a formal concentration of 0.0333 with an insignificant 3. And that gave an OH concentration of 9.24 times 10 to the negative 6 molar OH, and that is less than 1% of the formal concentration of A minus. So I got a pH from this OH concentration of 8.97, and again, I'm glad to see that the pH keeps on going up. Let's try one more place in the titration curve, and that'll be beyond the equivalence volume. So what's true now? Not only have we added enough OH to react with all of the HA in here such that HA is gone, we've added some extra OH. So we probably ought to figure out how many moles of extra OH there are. Again, I'll use an ice table to do that. So here's what my ice table looks like initially. Now, notice that HA is the limiting reactant. The moles of HA are less than the moles of OH. I guess I'm going to subtract those moles from the reactants and add them to the products so that at equilibrium, HA is gone and I've got excess OH, 0.00100 moles of OH, and I've made a little bit of the weak base. So let's think about this. Over here, we've got OH, which is a strong base. And over here, we've got A minus, which is a weak base. And yes, A minus can accept a proton from water to form HA and a little bit of OH. But do you think we need to worry about the little bit of OH that A minus can produce? Do you think it'll even come close to the moles of OH that you already have here? No, because this equilibrium lies to the left. So we're going to ignore the OH from A minus. So to get the pH, we just need to figure out this OH concentration. It'll be the excess moles that we've already calculated using our ice table over the total volume. You started out with 50, you added 35, and I'm getting an OH concentration of 0.0117 with an insignificant 6 molar OH and a pH of 12.071. Again, the pH keeps on going up. And the last thing we're going to do is sketch the titration curve. A titration curve is a plot of pH as a function of titrant added. And I guess I should have labeled this as the titrant. So this will be milliliters of OH. And remember how our pH kept going up? We started out acidic, and then we ended up in that buffer region, and we reached the equivalence point, and then we had excess OH. So here, to get that initial pH, we just used quick and dirty. We got away with that. And then here, we were in this buffer region. Remember, we were before the equivalence volume. Every time you added OH, it got consumed. All you had before the equivalence volume was HA and A minus, so we used the Henderson-Hasselbalch equation, but then you added just enough OH to neutralize all of that HA, and that extra drop of OH really made the pH shoot up. So this is called the inflection point, that place where the pH changes suddenly, and right in the middle here, this is how you would get your equivalence volume. So all we have in solution then was A minus, and how did we get the pH of A minus? Quick and dirty. The way that you would get the pH for any other weak base. And then beyond the equivalence volume, we just had excess OH. So sorry the video was so long, but this is really the only video I'm going to make for this chapter. Thanks for listening, and good luck.